So dot and cross diagrams can represent covalent bonds to show the sharing electron pairs. So for example, in chlorine, is Cl2. Each chlorine atom begins with 7 electrons in their outer shell. And by sharing one pair of electrons in the middle of those two chlorine atoms in a single covalent bond, it allows each chlorine atom to obtain a full shell, outer shell of electrons with 8 electrons in that outer shell. Another example would be water. So because oxygen has 6 electrons in its outer shell, it needs to have 2 more extra electrons shared with it to get a full outer electron shell. And to do this, in water, it forms single covalent bonds with 2 hydrogen atoms, and just so happens that each of those hydrogen atoms need 1 electron, so they can share a pair of electrons each. And you can also get double and triple covalent bonds. So the early examples we looked at were single covalent bonds, and only 1 pair of shared electrons were shared between the atoms. But it's possible sometimes to form to share 2 pairs of electrons, or even 3 pairs of electrons. So if you share 2 pairs of electrons, that's what's called a double covalent bond. And if you share 3 pairs of electrons, that's what's called a triple covalent bond. And those double and triple covalent bonds are normally stronger and require more energy to break, simply because they've got more shared electrons in between those atoms. And for each oxygen atom, it needs 2 electrons to get a full outer shell. Therefore, each oxygen atom shares 2 electrons with the other, then that leaves 2 pairs of electrons shared between the atoms. So remember that this is what we call a double covalent bond because it shares 2 pairs of electrons between the atoms. There are 3 types of covalent bond, remember. Single, double, and triple. And the single ones involved a single pair of shared electrons. And group 7 elements, therefore, are an example of somewhere where a single bond forms because each atom needs to gain 1 electron to gain a full outer shell. Double covalent bonds have 2 shared pairs of electrons. So an example of that would be group 6 elements. They're joined by double bonds to each other as the atoms need to gain 2 electrons to gain a full outer shell. And triple covalent bonds involve 3 pairs of shared electrons in the covalent bond. And you find those with group 5 elements. They're joined with triple covalent bonds because they need those 3 electrons to gain a full outer shell in their electronic structure. And remember those 3. A triple has 3 shared pairs of electrons, and that's between 2 nonmetals. A 1 pair shared of electrons between 2 nonmetals is a single covalent bond, and 2 shared pairs of electrons between 2 nonmetals are double covalent bonds. In hydrogen, which is H2, each hydrogen atom needs to get 1 extra electron to get a full outer shell of electrons. And each hydrogen atom shares 1 electron with the other, leaving 1 pair of electrons with a shared space between the atoms. So that's a single covalent bond. For ammonia, which is NH3, when the nitrogen reacts with the hydrogen to form ammonia, how many atoms will bond to each nitrogen atom? Well, nitrogen's got 5 electrons in its outer shell, so it needs to gain 3. But each hydrogen can only offer 1. So if we need to gain 3, you need 3 hydrogens in there to form a bond, to form the link and make nitrogen have the full outer shell and also have hydrogen have the full outer shell. Each nitrogen atom in N2, just so pure nitrogen, needs 3 extra pairs of electrons with it to obtain a full outer shell of electrons. So each nitrogen atom shares 3 electrons with the other, leaving 3 pairs of electrons in the shared space between the atoms. And that's an example of a triple covalent bond. Now, when we represent covalent bonds, there are many ways to do it. 4 ways of representing ammonia could be shown with dots. First of all, dots representing the outer shell electrons of atoms of one element, and crosses representing the outer shell electrons of another element. The limitation of this way of showing covalent bonds is that it only shows electrons differently for each atom when they're actually exactly the same. So even though an electron's coming from a hydrogen, or if it's coming from a nitrogen, they're actually the same thing, but they're represented differently. Another way of doing it is exactly the same, using dots for one atom's electrons and crosses for another atom's electrons, but not showing the rings around each of the elements. You can also use a ball and stick diagram. So the sticks represent the bonds between the atoms, and then there's balls which represent the actual atoms themselves. The only limitation of this method is that atoms are much closer together than the diagrams actually show. So it tries to show it in sort of a 3D structure, but it's not actually that accurate. And the last way that we can represent covalent bonds is using lines between atoms. So the atomic symbols, that's just the letters, represent the atoms, and the lines between the atoms represent the covalent bonds. So to recap those ways of representing covalent bonds, the diagram, a diagram that shows a dot and cross diagram would have the full outer shell of electrons, and it would have dots for the electrons from one atom and crosses from the electrons from another atom. And those 3 ways again, we've got the ball and stick diagram, we've got the dot and cross diagram with shells, we've also got the dot and cross diagram without shells, and then we've got the line diagram, which just has lines to show the covalent bonds. So, in hydrochloric acid, HCl, if you wanted to draw a dot and cross diagram for a HCl, you would have hydrogen, which has 1 electron in its outer shell. You could represent that with a cross, and then you could have the 7 electrons in chlorine's outer shell represented by dots, and between the hydrogen and the chlorine, you would have 1 cross and 1 dot. That's that 1 shared pair of electrons. And if we've got lines that represent a covalent bond, they're simply called line diagrams. Now remember, if we've got we can have 3 different types of covalent bond. We can have single, double, or triple. Now, single covalent bonds just have 1 pair of shared electrons between the atoms. Double covalent bonds have 2 pairs of shared electrons between the atoms, and triple covalent bonds have 3 pairs of shared electrons between the atoms. So the dot and cross diagram for hydrogen, H2, shows that 2 hydrogen atoms need to bond together. When these atoms bond covalently, how many pairs of electrons do they share? Well, it's a single covalent bond, and they're only sharing 1 pair of electrons. Both the hydrogen and the chlorine atoms need 1 extra electron shared with them to obtain a full outer shell of electrons in hydrogen chloride, HCl. Each atom shares 1 electron with the other, leaving 1 pair of electrons to be shared in the space between the atoms. And remember, that's what we call a single covalent bond.